Mercury has a day length of 176 days. Unless you want to stay awake for 117 days straight, then sleep for 59 days, we'll have to divvy this up. That's easy enough with such a large number because even dividing this day length into units of exactly 24 hours, which wouldn't be perfectly even with a day length, is alright. That's because with such long day lengths, day and night function more like seasons than day and night. And nobody needs the summer solstice or vernal equinox to be perfectly aligned with midnight. Even though sunset is very important on Mercury because of the sheer drop in temperature it causes, that date and time can be remembered, just like how we treat equinoxes and solstices on Earth. Counterintuitively, the trouble arises when we look at day lengths similar to Earth's. Well, more similar than 176 times longer. You see, at these shorter day lengths, it is more desirable for them to be split up or multiplied together by integers, whole numbers. Having two day lengths come together to form a unit is a lot more convenient than 1.5 day lengths coming together to form a unit. One is constant and easy for people to live their day by, while the other is inconvenient and tricky. Imagine if you knew that around noon and midnight it would be dark out, and that in the morning and evening it would be light out. That is the 2 days for one unit system. Now imagine that on one day the early morning and afternoon into evening was dark, while the later morning and late night would be light. The next day it would be switched. That would be the 3 days for 2 unit system. As you can see, integers are a lot more convenient. That means that next to using 1 day for 1 unit, the next best options are half a day for 1 unit for longer day lengths and 2 days for 1 unit for shorter day lengths. This is where the problem arises. We want units that are as close to 24 hours as possible. To determine the closeness of a unit, we will divide its length by 24 if smaller, and divide 24 by it if larger. The closer the number to 1, the better. The question is, at what point of being shorter than 24 hours is using 2 day lengths for 1 unit preferable than 1 day length for 1 unit? If we run the numbers, we find that the point is at a little under 17 hours, exactly 24 divided by the square root of 2. Going the other way, trying to find the tipping point for using half a day length per unit, we get a little under 34 hours, exactly 24 multiplied by the square root of 2. This gives us a range of day lengths we might have to deal with in space, 17 hours to 34 hours. The extremes of those ends are brutal to say the least. Let's start with 17 hours. Giving a 1 to 2 split of sleep and being awake, we get a little under 6 hours of sleep per night and a little over 11 hours of activity in the day. This would be like waking up at 6 a.m., then going back to bed at 5 p.m., then getting up again at 11 p.m., then going back to bed at 10 a.m., and so on. The main problem here is not the fact that this doesn't sync to an Earth day, because remember, it would line up to the day on this hypothetical planet. The problem is that people don't naturally get tired after being up for just 11 hours. Maybe the fact that they would only have 6 hours of sleep per night would make them sleep deprived enough to be tired after 11 hours, but it would not be good for their health. The opposite extreme that would have to be dealt with is 34 hours. This would require people to sleep for over 11 hours, then stay awake for nearly 23 hours straight. Imagine waking up at 6 a.m., then staying awake the whole day all the way to 5 a.m. the next day, then sleeping until 4 p.m., then staying awake again until the next day at 3 p.m., and so on. This would sync to the hypothetical planet's day, but would be like pulling an all-nighter and then crashing every day. Again, not good for human health. These two extremes only occur for 1 unit per day setups. Longer or shorter day lengths are freer because they have more integers to be multiplied or divided by. Therefore, they don't need to stray far from 24 hours before the next integer is better. But near 24 hours, the only integer options are 2 and 1, not very plentiful. This is a graph of optimal integer-based unit lengths versus day length. As you can see, the peaks and troughs tend toward perfection at 24-hour units as day lengths stray far from 24 hours. Interesting. It isn't exactly known what humans can comfortably use as day lengths, but 17 and 34 hours are definitely outside that territory. For now, let's assume a limit between 20 and 28.5 hours. With that restriction in place, we see that the units that have peaks and troughs outside that restriction are the 3 units per day, 2 units per day, 1 unit per day, half a unit per day, and 1/3 a unit per day. Also, we find that the celestial objects with uninhabitable integer-based units are Enceladus, Uranus, Miranda, and Neptune, with Jupiter and Ariel pushing the limit. For the objects that just push the limit, there might be only extreme mining and resource colonies, rather than residential ones. Also, for short unit objects, sleeping pills might be something everyone uses because they don't get naturally tired at the right time. And, for long unit objects, caffeine might be used to stay awake longer. Maybe some of these objects will have no other choice but to ditch integer-based units. Even though these 3/2 and 2/3 systems, as well as 5/2 and 2/5 systems, are inconvenient for when the sun is up, they are still predictable, just more complex. And it is better to be a bit inconvenienced than having an entire planet or celestial object be uninhabitable. All in all, day length is a very important factor to the habitability of a planet or celestial object. Humans are very sensitive to this factor, so some inconveniences will have to be dealt with.